You know that feeling when you stand at the base of a truly massive tree and you just feel tiny? It's pretty incredible. And it makes you wonder, right? Is there a limit? How high can a living thing actually reach for the sky? Well, today, we're going to find out. So that's the big question we're tackling today. We're going to explore the absolute physical and biological limits that stop a tree from just growing forever. And, this isn't just about getting lucky with good soil. Nope. It's a high stakes battle against the laws of physics itself. So here's how we're going to break this down. First, we'll look at this whole thing as a race to the sky. Then we're diving into the three massive hurdles every tall tree has to overcome. You've got the water lift, the force of the wind, and its own energy budget. And then, at the end, we'll see exactly where all those challenges meet to give us the final answer. All right, first up, this race to the sky. The thing you gotta get is that a tree's height isn't random at all. It's the result of this fierce internal balancing act. It's got the need to reach sunlight on one side, and on the other, the huge challenges of just existing at that scale. You can almost call it a three-front war. And these are the three fronts of that war. You've got hydraulics, that's basically the tree's plumbing system. Then there's mechanics, which is all about its structural engineering, how it stays standing. And finally, something we can call carbon economics. It's really just the biological need to make sure growing tall is actually, profitable. Let's dive into the first one.
Okay, so let's get into our first major challenge, and trust me, it's a big one: water. Think about it. Trees don't have hearts, they don't have mechanical pumps, so how in the world do they get water from the roots all the way up to leaves that are hundreds of feet in the air? Well, they don't push it, they pull it. As water evaporates from the leaves, it creates this incredible suction that pulls a continuous but really fragile chain of water molecules all the way up the trunk.
But here's where the danger comes in. If that suction, that tension, gets too strong, tiny air bubbles can form inside those water columns and snap. The chain breaks. This is called cavitation, and it is just like a deadly embolism or a heart attack for the tree's plumbing. It's basically the silent killer that haunts every single tall tree. And this number right here, this is the core of the whole problem. For every single meter a tree grows, gravity adds this constant extra tension. Now, to put that number in perspective for you, a car tire is usually around 0.2 megapascals. So yeah, 0.01 is a small number on its own, but it's this constant, relentless tax that just builds and builds and builds over 100 meters. It makes the risk of that deadly air bubble worse with every single inch of height. So what does a tree do? It's faced with this huge design dilemma. It can build narrow little pipes, or conduits, which are way safer against that cavitation problem, but they're not great for moving lots of water. Or it can go with wide conduits, which are super efficient at water flow, but they are much more likely to fail under all that tension. It's this constant, high-stakes trade-off between safety and efficiency. And you can actually see the results of this struggle. If you look at the very, very top of the world's tallest trees, you can see them hitting their limit. The leaves up there, they're smaller, they're thicker. The tree's controlling water loss way more carefully, and because of that, photosynthesis per leaf is actually lower than it is further down. The tree is, for all intents and purposes, physiologically screaming that it just can't pull water any higher. Okay, so that's the water problem. On to our second major challenge, just pure brute force. A tree isn't only a plumbing system, right? It's also a massive biological skyscraper that has to somehow withstand gales, hurricanes, and the constant push of the wind, all while being stuck in one spot. Yeah, engineers actually have a perfect term for this. They call it a tapered cantilever. Basically, it's fixed at one end, the ground, and it has to endure these immense bending forces at its base. And those forces just get magnified the taller and taller it gets. It's a truly monumental structural engineering problem, and the tree has to solve it with nothing but wood and roots. And this is the absolute key right here. A tree's design isn't for an average, calm, sunny day. No way. Its maximum height is set by its need to survive the most violent, brutal storm it might face in its entire centuries-long life. It has to be built for the absolute worst-case scenario. And to pull this off, trees have evolved this incredible structural toolkit. For one, they taper, right? They get much wider at the base to handle all that stress. They also develop these massive, flared buttress roots to give them a stable foundation. And get this. They can even grow a special kind of reaction wood to actively push back against leaning and reinforce any weak spots. It's pretty amazing. All right, so we've got plumbing, we've got engineering. Now for our third and final challenge, the simple economics of the whole thing. Because at the end of the day, growing tall has to actually be profitable for the tree. This really is the fundamental rule. The energy a tree gets from sunlight, let's call it its carbon income, has to be greater than the energy it spends. And it spends a lot. It's building and maintaining this massive trunk that can't photosynthesize, a super complex root system, and that incredibly risky plumbing we talked about. Bottom line, height has to pay for itself. And this really lays out the whole dilemma, doesn't it? I mean, when a tree is young, the benefits of getting taller are huge. You get more sunlight, you outcompete your neighbors. But as it grows, the costs just start to skyrocket. The risk of that hydraulic failure goes up, the risk of wind damage goes up, and the sheer amount of carbon you have to invest in building a thicker, stronger trunk becomes absolutely enormous. This all creates a kind of feedback loop. A tree grows taller for more light, but that means it needs a stronger structure and better plumbing. That requires a bigger carbon investment, which means it demands even more photosynthesis to pay for it all. And around it goes. This loop is what powers its growth, but, and this is the whole point, eventually a time comes when the costs just get too high and they outweigh the gains. The whole loop just breaks.
And that right there, that breaking point, brings us to our final section. We've seen the three great forces holding these giants back: the physical limits of moving water, the constant threat of the wind, and this biological law of diminishing returns. So now, let's put it all together and find our answer.
So the big question is, where is that point of failure? At what exact height does the math just stop working? Where do the combined risks and costs get so ridiculously high that growing even one more foot isn't a benefit anymore? It's a liability. And here's the answer. When you take all of it, the hydraulics, the mechanics, the carbon balance, and you put it into the models, they all point to the same number, a theoretical maximum height of around 130 meters. That's roughly 425 feet, and that is the absolute limit, assuming the most perfect, ideal conditions anywhere on Earth. That's the ceiling. It's the point where the very top of the tree is living right on the edge of deadly cavitation, where the trunk needs a ridiculously expensive amount of wood to stay upright, and where the energy coming in from photosynthesis just can't pay the bills anymore. The tree, quite simply, cannot turn a profit.
And that leaves us with one last, kind of fascinating and maybe a little worrying thought. These limits we've been talking about, they aren't set in stone. In a world with hotter droughts and more intense storms, those physical and economic limits are going to shift. And it really makes you wonder, doesn't it? Will the giant trees of tomorrow actually be shorter? Not because they can't grow tall, but because our changing planet simply won't let them?